Welcome to statistical modeling. This video discusses the simplest of all random effects model, mixed effects model, the one that includes basically only a random intercept. Okay, and so that corresponds more or less to the case we had in the first video of this chapter, which was about including a group-specific effect. But here, rather than specify a coefficient for each of the variables, we're going to allow it to have a random effect bi that's going to be group specific. So here bi is associated to the intercept. Okay, so that's as before. So we're assuming the errors have some covariance structure. Most of the time it's the identity, but here I'm just going to have one random effect. So the intercept that's specific to group I, the conditional mean of y, that's beta naught plus bi. Okay, and here the slight difference of interpretation relative to the model with a group effect is that now I have beta naught is the common effect over all group. Okay, and bi is group specific, so the average of the bi is 0, but every group gets 1. So there's no baseline here. Okay, it's really beta naught is the common effect overall, and bi is the sort of group specific deviation from that, which is mean 0. So what does it look like? Well, here I fitted the model with, for simplicity, I'm just putting t as a fixed effect. Okay, so none of the other covariates, and I'm representing the revenge score as a function of time. Okay, so questionnaire wave goes from 1 to 5. On the left, you have the individual trajectories, so the actual observations, and on the right, we have, on the left you have the slope and the intercept, so the overall intercept beta hat naught is something like 4.6, and then there's a negative slope of about minus 0.56. And now you can see on the right we've added a random intercept. So every individual, every of the 80 person gets a different intercept that's centered around this 4.65. And the slope is the same for everyone, but now they're allowed to vary. Okay, so you can see this as the prediction. We'll cover this in an upcoming video. So the random intercept kind of achieves what we were aiming for, which is to let people who start, some people have a higher original score, so we think that the decay is pretty much the same, but I want to allow them to start at different levels. Okay, and of course that model is not perfect because we haven't constrained the response to be between 1 and 7, but not much harm done. So random intercept, that's a special case of the general linear mixed model we've covered in the previous video. So here I have M group, so I'm going to have basically I'm just going to denote B1 to Bm. Okay, so these are the individual effects that are associated to the intercept for each of the M groups. Okay, so if you think revenge data, we have 80 groups. These are 80 such random variables, and I have now error terms and some explanatories. I'll assume that these BIs are independent normal, so they'll all be mean 0. They have the same variance, sigma square b, and there's errors, so epsilon ij, that I'm going to assume for the time being are independent, okay, between group and within group, just for the sake of argument. So BI is random, so it induces within group correlation, and that the way it does it is the following. So epsilon I and beta I are independent, so if I look at the variance of y, then there's the part with x betas, and that's not varying, so the variance there is 0. Okay, these are constant. I'll pick up the variance of the BI plus the variance of epsilon ij, and then they have 0 covariance because they're independent. So the variance of BI, I've assumed that's sigma square b. The variance of epsilon ij, that's sigma square. Okay, and so the covariance between two individuals in the same group, that's just going to be sigma square b, because two people that are not the same, well, the variance of epsilon ij, that's sigma squared, but the covariance between two, because they're independent, that's 0. Okay, so I get the same thing but without the sigma square. So I have the variance, I have the covariance, they all have the same, they're all homoscedastic, so the correlation between two individuals within a group amounts to sigma square b over sigma square plus sigma square b. And this quantity is often called the intraclass correlation. Now this should look a bit familiar to what we had before. Okay, so I'm just going to rewrite it in a slightly different manner. So this is the covariance in general, that's how you would derive it. And if j equals k, you get sigma square b plus sigma square. Otherwise, you just get sigma square b. Okay, so here is the mathematical side if you want to have a look. And if you wanted rather to consider the full covariance matrix of group I, okay, you could just write it down in matrix form. Okay, so we had seen in a previous video that the variance, the marginal variance of y, that was z. Okay, so here the matrix of random associated to the random effect, that's just a column of 1. Okay, and here the actual omega, that's sigma square b, that's just 1 by 1 matrix. So I can pull it out. And then I get 1 transpose, which is a matrix of constants with 1. I multiply by sigma square b, I get a full, basically a matrix with all the entries equal to sigma square b. The errors are independent, so it's just plus the variance of the error, and the errors are independent from one another, so they have variance sigma square times the identity. And so when you look at this, basically we're really decomposing the total variation, the one that's due to the comment bi term, which is random, and due to the error. And if I add the two, you get the compound symmetry model. Okay, so that may seem like a lot of complication just to get a compound symmetry model, but actually it's not the same. So you'll get the same parameter estimates, you'll gain the same fixed effect, yes, but the model's fundamentally different. On the one hand, you put everything, so if you wanted, in the previous chapter when we look at this, we basically had no random errors. So the term on the left, that was just zeros, and everything was on the right. Okay, but now nothing prevents me from adding a structure for the error and adding something for the random effect, and that's going to induce more variability and different structure for the covariance. So this is much more general. Okay, but if you put a random intercept with groups, that adds a compound symmetry somehow to the lot. Okay. The slight difference here is because we're assuming these are random effect. The sigma square b, as the square indicates, it's a variance, and this parameter has to be positive. Whereas before, the correlation could have been slightly negative. Okay, there's a lower bound because there's all these row entries, so there's actually some limitation. But here, the fact that we're restricting to positive correlation is actually not practically significant, because if you're looking at within group correlation, they tend to be positive. Okay. So the important part, how do we fit this model? So before we use the repeated line call to specify the covariance for the errors, we still do that, but here we're just going to not care for the errors. We're just going to assume that they're independent for now. So if you don't specify repeated, they're just assumed to be diagonal independent, and you can read this from the output to make sure that it's indeed the case. So proc mix, I'm going to use the motivation data to just show you the output. So class here ID unit, I'm going to ask for the solution so I can have the table with the parameter estimates. And here I'm going to add, so as I said, repeated, because I don't want structure on the error, I'm just going to leave it, I'm not going to specify it. And now I have random. Okay, so this random, on the left, you say random, and then you put all the explanatory variables for which you want random effect. So if you wanted a random effect for sex, you would put intercept and sex. I mean, if you usually intercept corresponds to group effect, so that's typically the one you want. But if you wanted more, you would include those variables next to that. Slash, still subject, okay, so you have to specify what's the group. And here v equals 1 and v core equals 1, that's basically going to say print the covariance and the variance and covariance matrix, and the correlation matrix of ID unit 1, and that corresponds to the marginal variance of y. Okay, so that's the sum of the variability of the error and of the random effect. Okay, and this naturally, so you don't have to specify type equals yet. The fact that you have a random intercept naturally induces the compound symmetry. And here is the matrix, and if it sounds familiar, well, it's because it's exactly the same coefficient estimates as we had before. Okay, 0.24 for the sigma square, which is the errors variance. Sorry, no. 0.24, which is the covariance. That's the variability of the random intercept. Okay, so the group specific variability in terms of motivation score, that's 0.24, whereas the overall variability for the residual is 1.12, and you can compute the within unit correlation, and that's exactly the same we had with the repeated command and the compound symmetry model. And likewise, the parameter estimates are exactly the same. So both models are equivalent, but as I said, this is a special case. Linear mixed models are more general than just fitting compound symmetry models. And then we can get predictions for units, which we couldn't do before. Stay tuned for that.